In today's note, we're going to be looking at continuous random variables. So, in the past, we've studied discrete probability distributions for discrete data. So this is where, again, it was more counting values. And this produced a bar graph of probability distributions. So this could be something like rolling a die or finding the sum of two die, because again, those outcomes were discrete. There were no range of values. It was either one thing or the other. So when we look at continuous variables, again, they take on a range of real numbers. So if we're looking at fractions, decimals, length, time, etc., again, we want to be careful with the decimals, as we've seen in the past, but in most cases, decimals would indicate continuous. And the probability for continuous variables is calculated by finding the area within a distribution interval. And we'll look more specifically at what we mean by that. So the probability distribution graph below is represented with a continuous smooth curve. So this will represent continuous data because it's a range of data, so all values are usually, or an interval of values, are taken into consideration. So we now find that the probability of x falls somewhere into a range or an interval, not a set or specific values. So like we saw before, the probability was specifically a certain value. Here it's now going to fall between a range of values. So if I look at my probability distribution graph for continuous variables here, and I'm looking for the probability of between A and B, the area underneath the curve, or underneath my graph, gives me the probability. So I have to be able to determine the area underneath a curve or underneath a graph, and that will give me the probability of an event occurring. So for any probability distribution that we look at, the total area under the curve is always equal to 1, since it represents all outcomes. If the line represents all possible outcomes and the area underneath the curve represents the probability, we know that the total probability is 100 or 1. So there are 5 main types of distributions that we may see. The first one is the unimodal distribution or one-mode distribution. This is also considered a normal distribution. It could be called a bell curve, or mound, but a standard distribution which occurs naturally in a wide variety of settings. And the mean, median, and mode are all very close together. So in this case here, we would see that in the middle, we would have our mode, our median, and our mean, all very close in the middle, where we have our probability on the y and our values, or x, on the x-axis. So this is a unimodal distribution. Secondly, we would have a bimodal distribution. Bimodal distribution usually indicates more than one population being tested, and basically we see two modes or more. Usually it's only really 2, but we can see here that we have one mode and we have another mode, or 2 that occur the most. So we see this kind of hump or this kind of camel looking graph. For number 3, positively skewed distribution, we've seen this before in the last unit as part of the homework, but this typically occurs in populations where there are a larger number of positive outliers. And in this case, the mean, which we can see here, is usually greater than the mode, which we can see here. So you could also call this, instead of positively skewed, you might see it called as right skewed. And basically how you can determine if the graph is that, basically you look at the tail. Wherever the tail is tells you what type of skewness it is. So the tail's on the right side, so it's right skewed, or it's in the positive end, so it's positively skewed. Basically, you just look at the tail. Or basically the end of the graph. For our negatively skewed distribution, opposite of positively skewed, so positively was right, so negatively would be left skewed. And this typically occurs in populations with a larger number of negative outliers. Similar to the last one, positively skewed, it's going to be the opposite. So rather than the mean being greater than the mode, in this case the mean is less than the mode, as we can see in our graph here. Again, just a rough example of it. And lastly, our last distribution, or the simplest one, is called uniform distribution. So we've seen uniform done before in uniform probability, and when we were looking at discrete data, we would see something similar to this if we were to draw our probability distributions. So there was 1, 2, 3, 4, 5, 6. So these would be the outcomes 1 out of 6, because each outcome is equally likely for rolling a die. Again, the key thing here, there's no touching between the bars, right? Discrete data, they're separate. There's no range or interval, so it is a bar graph and they do not touch. Now, if we're looking at continuous, it looks almost identical, except it would look something like this. So we would have all the bars touching each other because it is a range, or there is continuous data, so it goes from anywhere between 0 and 1, 1 and 2, 2 to 3, and 3 to 4. So it includes all values between 3 and 4, or in this case between 0 and 4. Whereas with discrete, it was only 1, only 2, only 3, only 4, only 5, or only 6. So that's the key difference between how they look. So the bars touch this time because we're talking about all the values from one number to the next. And what we should be able to see is we do still see something similar in that they do all kind of form a box shape. Even if I look at the discrete data, I see the box shape. And the reason I see the box shape is because, as we know, all outcomes are equally likely. That's why we get the box shape. So, as an example, if I want to try to determine which will have a continuous probability distribution, I need to look at my scenarios and determine, am I going to be looking at continuous data or discrete data? So if I look at the length of a cut piece of wood, this would be considered continuous because in terms of measurement, I could have a wide range of measurements. It's not just going to be specifically set values. For the number of marbles in a bag, this would be discrete because again, there's only set numbers. It's not going to be a range of values. For example, I'm not going to have 1 to anywhere between 1 and 2 marbles. It's like 1.1, 1.2, 1.3, and so on. So it's going to be simply either 1 or 2. For C, same with as the last example, it will be discrete because the number of children will be a set value. It's not going to be a range or an interval of values. And finally for D, the mass of fish caught, because it's a measurement and we could have a range of values. So it's not going to be specifically just 1 pound or 2 pounds. It could be anything between 1 and 2 pounds. It would be continuous data. It would be a continuous probability distribution. In example 2, we're going to take a look at using a probability distribution graph for continuous variables. So the Allenberg Bridge takes 10 minutes to raise and lower. X represents the waiting time for the bridge. We want to construct a graph for this distribution. Because we're dealing with time, it has to be a continuous variable or continuous probability distribution graph, because time is a continuous value. What we want to do, though, is we want to assume uniform distribution. And the reason we want to assume this is we want to assume that it's all equally likely of the bridge raising and lowering. So I have my values here, or my variables on my graph: probability, density or probability, and the time. So when we're drawing a graph like this, or to graph the probability density for a uniform function, the height of the graph must be known. And since the total area under the curve must be 1 for all the probabilities, they all add up to 1, the height is given by h, or the height, times b minus a, or my range, is equal to 1, or the height is equal to 1 divided by b minus a. So basically what this works out to, we talked about before that the probability, or the area underneath a curve, is considered the probability. In this case, because we know uniform distribution forms a box, the area underneath the curve is length times width. So that means that the probability is equal to the height of my graph times the range of values, so b minus a. Or if I want to figure out, or I know that 1 is equal to h times b minus a. So again, that's where we get this where we get these values. So if I look at my graph, I know it has to form a box. So I'm just going to draw my box like so. So basically I have ranges from 0 to 5, from 5 to 10, and from 10 to 15. Those are my range of values. But I need to figure out what my height is on my graph. So I know that my height is going to be equal to 1 divided by b minus a. And if I look at my values, it ranges from 0 to 20, and this is going to be my b minus a. So basically it's saying it's equally likely between these points. So that means I have a range of 20 values overall. So I do 1 divided by 20 minus 0. I get h is equal to 1 out of 20. So that means that my height, in this case of the graph, is 1 over 20. So that means it doesn't matter where or what time I'm at, the probability is 1 out of 20. Or the probability that I'm going to be waiting any amount of time is 1 out of 20. So for B, what is the probability that you will wait 5 to 10 minutes? Well, if I go back and I look at my graph, I know it went from 0, 5, 10, 15, 20. I know that the height was 1 out of 20, or that was the probability for any value. It was 1 out of 20. And when I'm looking at this, I want to find what is the probability that I'll wait between 5 and 10 minutes. So I'm looking at the area underneath my graph between 5 and 10 minutes. So that means any number of time between 5 and 10. 5.1, 5.2 minutes, 5.3, 6.3, whatever it happens to be, any value between 5 and 10. So if I'm trying to find the probability of between 5 and 10 minutes, I need to find the area underneath this curve, or this line. So in this case, it will be length times width. And when I look at it, my length, in this case my height, is 1 out of 20 times my width. So the width is a range of from 10 to 5, so I'm going to do 10 minus 5, which is equal to 1 over 20 times 5, which is equal to 1 out of 4. So therefore, there's a 25% chance you will wait 5 to 10 minutes. So the key thing that we need to get out of this note is how we're dealing with now continuous variables, and the idea that when we have a continuous probability distribution, the area underneath the line represents our probability. And when we're dealing with uniform distribution, we can figure out the probability of by doing length times width. We can also figure out the probability of an event occurring by taking the range of values and dividing 1 by it. So that means that each outcome has an equally likely chance of occurring.